All right, chemistry, let's look at your worksheet for section 2. And we're going to be answering questions about oxidation numbers here. Start with number 1. Assign the oxidation number to the specified element in each of the following examples. So starting with A, sulfur in an H2SO3. Now we have a few special circumstances here. We have hydrogen being in front, so it's going to be a +1. We have oxygen in its most common form, which is a -2. And the reason I know that is because it is not paired with fluorine, and it's not in a peroxide. So it's going to be a -2. Now I have 3 of -2s, so that's a total of -6 on that side. I have 2 of these +1s, so that's +2 on this side. So in order to make these balance out, I am going to need sulfur to have a +4. Now I'm looking at sulfur in MgSO4, magnesium sulfate. So again, most electronegative thing here, oxygen, -2. Magnesium only has 2 electrons to pull on, so that's going to be a +2. Now again, don't make the mistake of thinking, okay, well, sulfur is going to have a 0 oxidation number because these already balance out, because there are 4 oxygens. There are 4 of these -2s. So that makes a total of -8. So in order to balance these out, in this situation, sulfur needs to be a +6. And I want to point out here that we're looking at sulfur in both examples. They don't have to be the same number. For example, when I was talking through oxygen right here, the most common version of oxygen has an oxidation number of -2. But when it's bonded with fluorine, it has a +2, and in a peroxide, it has a -1. So even in oxygen, we see that oxygen can have a total of 3 different oxidation numbers depending on the situation that we find it. Is it with a peroxide? Is it in a molecule with fluorine? Or is it in its most common form where it's the more electronegative element in that compound? So look at C. Again, sulfur yet again. But this time we see we don't have any special circumstances. Okay, there's no hydrogen, there's no fluorine, there's no peroxide, and there's no pure element. Okay, so none of these things are present. So I'm just going to find the more electronegative element, that's sulfur, and I'm going to give it an oxidation number of -2, because that's the charge that sulfide would have. Right? If sulfur were to ionize, it would be a -2 charge. And when we're looking at the more electronegative atom within a compound, that's the number we assign for the oxidation number. Now, I do not actually have to find out what the oxidation number of potassium is because C is asking for sulfur. And again, we've looked at sulfur 3 different times. We have 3 different oxidation numbers. Now, typically, this is the maximum number of oxidation numbers an element can have. Typically don't see this much variation, but we are going to see variation, so don't think that they're always the same. We got copper in Cu2S. Again, we just identified that sulfur is going to have a -2 oxidation number. I know that because it's the more electronegative atom after I double check that there aren't any of these special circumstances. And in order to balance out this -2, this whole side, okay, these 2 copper atoms have to contribute a +2 in order to balance out. But there are 2 copper atoms, so that means each one is going to be a +1. Down here we have a sodium chromate. So we're looking for chromium here. Now sodium is in main group 1, so it has a maximum 1 electron to pull. So that's going to be a +1 oxidation number. Oxygen is in its most common form, so it's going to be a -2. There are 4 of them, so that's a total of -8. There are 2 of these sodium, so that's a total of +2. In order to balance these out, I need a +6. The other thing I want to point out, sulfur and chromium are not in the same group. Okay, a lot of times when we look and try to figure out ionic charges, we look at the group number. It doesn't work here in oxidation numbers because it's relative to what other elements you're bonded to, and that is going to affect your oxidation state. All right, F, looking at nitrogen here. I have a special circumstance. I have the hydrogen. It's in front, so I'm going to give it an oxidation number of +1. I have 3 oxygens. I'm going to give each oxygen a -2, so that's a total of -6. So in order to balance these out, I'm going to give nitrogen a +5. Moving on to G and H. I want to point out there is something different about G and H. We have what we call formal charges, overall charges. Okay, so this entire species has a -1 charge. This entire species has a +1 charge. So in A through F, we were trying to make sure that the positives completely balanced out the negatives, so that we would have an overall oxidation state of 0. Here we're not going to do that anymore. Because this is telling us a -1, we're going to shoot for an overall oxidation state of -1. And here we're going to shoot for an overall oxidation state of +1. That's all these mean. If this was a -2, I'd shoot for an overall oxidation state of -2. Right? +2, I'd shoot for a +2. But we're looking for carbon here. I see I have a special circumstance. I have hydrogen in front. I have common oxygen, so it's going to be a -2, but there are 3 of them, so that is -6 and a +1. Now, if I was going to normally try to get these things to balance out, I would need a +5. But I'm not trying to get a perfect balance out. I actually need to be at a -1, So I'm not going to have a +5. I'm going to have a +4. And that will leave me with an overall oxidation state of -1. H, we're going for the +1 here. We're going for the +1. We're looking for nitrogen. Notice we've already looked at nitrogen in F. It's not going to be +5, just a spoiler alert. So we have a special circumstance. We have hydrogen, but here it is in back. Okay, it's in back.